Hello, in this video, we are going to be talking about the phases of matter. Now, you might already be familiar with the phases of matter. In this video, we're going to talk about it from a chemist's perspective. How do chemists view matter and the phases of matter? To start, let's talk about an important theory that we need to understand how matter behaves. So this is called the particulate theory of matter, and it states that all matter is made of small specks, tiny little bits that we call particles. And to sort of demonstrate that matter is made of particles, if you take water, which we consider, from our everyday observation as something, say, continuous, but we put it in a spray bottle and spray it, we see that the spray coming out, the water has actually turned into tiny little bits. It's sort of breaking up. And so we can call these little bits particles, and we know that water therefore must be made of small bits called particles. Now, this is a little bit misleading because the actual particles we're interested in are a lot smaller than this. And so to give you an example, with the technological advances in the last few decades, we have microscopes small enough to see the actual particles of matter. And so this is one image of a single particle of a substance of matter. And it's this sort of long object here. Now the scale is shown here. It's 5 angstroms. An angstrom is 1 times 10 to the minus 10 meters. So we're talking about extremely small particles here. And something that we can't see with our eyes. Unfortunately, we'll always have to use some kind of instrument to understand or to visualize, I should say, to actually see these particles. But the good news is that through observations of phases, we can get an understanding of how particles behave. So even though we can never see them with our own eyes, we still have the ability to observe them by seeing how they affect the phases of matter. But to get a little bit more specific about what we mean about particles, what we say is that the tiniest of tiniest particles of matter are atoms. So this means particle is a generic term. It just means a little speck of something, but those particles could be atoms, which we call the fundamental unit of matter, and they're usually represented by dots on the paper. And when atoms come together, we say they bond and connect into larger particles. So this is now a new particle made of 3 atoms. We call this a molecule. So to go back to the image that we saw, this particle is depicted using this sort of image, this cartoon. We see the individual atoms that are connected to make this molecule. So we see white atoms and gray atoms form this molecule. They sort of arrange and connect in little hexagons to make a molecule. So this is what we mean when we talk about particles. They're either atoms, which are the tiniest of tiniest specks, or they're molecules, which are the atoms connected together to make larger particles. Now, what we're going to do is connect our observations of the phases of matter to what we can interpret as the behavior of the particles. So in other words, we have some everyday examples of the phases of matter, solids, liquids, gases that you see here. And our goal is to say, well, because there are differences between how solids behave and liquids, that must mean something about the particles in that substance. And that's the whole idea behind the particulate theory. The idea that from the behavior of the tiny particles, we can understand the bigger picture, the phases, and we can also go in reverse by understanding how the phases look, behave, sort of our observations of them, we can understand particles better. So I have a little experiment comparing the phases. All I'm going to do is I'm going to take an example of a substance of each phase of matter. and I'm going to transfer it from a large container, so 5-liter container is the size, to a small container, a 1-liter container. And what I'd like us to do is make observations. Do we conclude, based off of moving the object from one container to the other, that this phase of matter has a definite shape? It has a specific shape, a definite volume, meaning a constant volume. It's something that doesn't change when I change containers. And is the substance compressible, meaning can I force this kind of matter to be a different volume? So let's try the first one together. So I have a solid, so it's a gold cube. Now what I'm going to do is I'm going to take this gold cube and I'm going to put it in the 1-liter container. This is going to help me determine whether or not I can make conclusions about these 3 possible observations. So taking a note, I'm going to move this over here. Oh, the way I've drawn this gold cube, it actually does not fit into the container. No matter how hard I push, it will not go in. And in fact, my pushing does nothing to the shape of this cube. So what can we conclude about our observations of solids? Do solids have definite shape? Well, the shape didn't change. Yes. Does it have a definite volume? Well, the size of the cube does not change just because I change containers. It has a definite volume. And is the substance compressible? No matter how hard I try, I cannot squish the gold cube into a smaller size. Its volume remains constant. So the fact that it has a definite volume means it must not be compressible. The two kind of go hand in hand with each other. So that's how this works. Okay, let's try it again with the liquid. I pour maybe a glass of water into the container, and now I'm going to pour it into a new container, and you tell me about these possible observations. So, does the liquid have a definite shape? Comparing the two? No, it fits its container. Does it have a definite volume, however? The amount of space it takes up is always the same. So the answer is yes, it does have a definite volume. Its volume is always the same. And you might be saying, well, it looks different, so how is it the same volume? Well, think about it like this. The volume is length times width times height. Or in the case of this cylinder, it's going to be the area of the base times the height. What we've done is that when we transfer it into a smaller container, the area of the base has gotten smaller. But what happened to the liquid's height? It got larger. So the base goes down, but the height goes up. So base times height actually ends up being the same because one went up, the other went down, and they kind of cancel each other out. So from this, we see that the liquid has a definite volume. Now, if a liquid has a definite volume, does that imply that we can or cannot squish it into a smaller space? It means we cannot. If it has a definite volume, then that means we cannot change it without doing something severe to it. So that would be our answer for the liquid. And then for the gas, I put maybe a balloon of helium gas. I empty it into this container, and then I quickly pour it into the smaller container. Does the gas have a definite shape? Much like the liquid, it does not. Does it have a definite volume? Well, the gas fills up its container, so it makes 5 liters. But if I put it in the 1 liter, it fills up until it reaches 1 liter of space it's taking up. So it actually does not have a definite volume. Now, what about, is this substance compressible? Meaning, can we squish it? Well, we just have. We've taken this 5 liter volume and we squished it into a 1 liter volume. Gases are compressible. Now, what I want us to connect this to is, what does this mean about the particles? And there are two conclusions we can make about the particles of these phases. One is how spaced are the particles, the relative spacing between particles. Based off of what we saw about maybe the squishiness of our particles, we might be able to make a conclusion. And then finally, how about the relative kind of movement that our particles might be capable of? So freely moving, meaning goes wherever it wants. Restrictive movement, so think maybe more like they can really only like slide around, so not necessarily going everywhere. And then minimal movement, in other words, vibrate. So if you can't really move, all you can really do is sort of shake back and forth. We call that vibrate. So go ahead and brainstorm what you think would be your answer. What are the particles doing in a solid based off of your observations here? How about liquid? How about gas? Go ahead and pause it. Okay, so you thought about it. Now we're going to complete a table to make sure that we have our understanding connected. So what distinguishes the phases of matter? So these are our macroscopic view, of, in other words, what we can see with our own eyes, and then the nanoscopic view, what we cannot see because it is very, very tiny. So solid, shape, is it definite, indefinite, volume, compressible, and then what did you have for the space between particles, type of movement? If you haven't already done this, go ahead and fill out with what you think the answers are. Pause the video now, and I'll return to discuss what we have. Okay. So as for shape for solids is definite, liquid indefinite, gas is indefinite, volume, okay, and compressible, no, no, yes. So these were all the answers we talked about in the last slide. Now, what about your answers? Because of these behaviors you observe, is there a lot of space between particles or not a lot of space? Is the movement free or is it not free? So what did you say? And so forth for the liquid and the gas. So let's do the space first. What did you say here? So solid should be closely packed, meaning there's not a lot of room for them. Liquid is they're restricted, but there's sort of room to slide. And the gas, because we could compress it, it must mean there's a lot of empty space between the particles. So there's a lot of space between the particles. They're very far away from each other. The type of movement, vibration is for a solid, not a lot of room. And so we expect them to only be able to move back and forth, back and forth. Liquids, because they pour, because they flow, they could slide past each other, but they don't expand all the way to the top of their container like a gas. The gases are freely moving. Okay, so those are our phases of matter. And I'd just like to mention a few sort of finer details about the phases. Starting with solids. So there are two types of solids. Solids whose particles are organized in a repeating pattern are called crystalline. And here's an example that you might be familiar with, sodium chloride or table salt. If you ever take a moment to sort of look very closely, you could see it with your naked eye, that sodium chloride or table salt has a very geometric cubic shape, looks like a cube. That's because its particles are repeating in a pattern that looks like cubes stacked on top of cubes. But you might not be familiar with the fact that metals are crystalline solids. We don't really think of a metal as a crystal. It doesn't really come to our minds. But one example to show that they really are is that if you take a look at copper, and this is copper that's made through electroplating, which is a technique that uses electricity to form metals, which we cover in a later semester. What you'll find is that you actually see that copper looks like crystals. And that's because the copper particles, these are copper atoms, stack in a very specific geometric looking pattern. Solids whose particles are disorderly are called amorphous. And an example would be rubber. Rubber is a solid, like a rubber band, but it can sort of be deformed a little bit, meaning we can kind of bend it and so forth. And that's because even though its particles are closely packed together and only sort of vibrate in place, there's some kind of bends to it where there are little gaps, which means that we can kind of manipulate, change the matter a little bit. So solids can be either crystalline, nice and orderly, or amorphous, still close together, but kind of random. Liquids and gases. So one thing is we want to be able to connect the behavior of liquids and gases to their particles. The fact that I can turn over this container of, say, olive oil and it flows tells me that the particles can slide. This is a substance called iodine, and it's turning from a solid to a gas. So we call it subliming when it does that. And we see that because it's wispy and moving in all directions, we know something about the particles. They're freely moving, spreading apart, and so forth. So you should be able to describe what the particles of a substance are doing based solely on what phase the substance is. If I know it's a gas, I know what the particles are doing, how they move, how they behave. That's the goal of this. So recap. All matter is made of moving particles. The spacing between particles determines the phase. But one question is, why do water particles, for example, stay close together while helium particles do not? So example being a glass of water versus a container of helium. What we say is that all particles have some attraction to each other. The more attracted particles are, the more likely they will stick to one another. So based off of what we know about liquids versus gases, does liquid water have more attraction, or does gaseous helium have more attractions? So we would say that water molecules are stickier for one another, and that's why they stick closer together and become liquids at, say, room temperature. Whereas gases, they're not that sticky for one another. There's not much attraction. So they freely move away from each other. And that's why helium is a gas at room temperature. In summary, particulate theory means that all matter is made of moving particles. Phases result from the collective behavior of a substance's particles. They're working together, they make a solid, a liquid, a gas. We can make conclusions about the macroscopic/nanoscopic based on our knowledge of the particles. So going back and forth, if I know it's a solid, I know this about the particles. If I know this about the particles, I know that it should be a, for example, gas. The tendency for a substance to be a certain phase at a given temperature depends on particle attractions. Okay, so thus concludes our video on particulate theory. We'll cover more in lecture.